Now that we have a notion of how to calculate changes in entropy for various kinds of change processes, let's look at one that will give us some insight into the character of entropy. So I'll remind you once again that a differential change in entropy is defined as the incremental change in reversible heat divided by the temperature. Now what I want to do is I want to test this process by looking at both a reversible process and an irreversible process. And the way I'm going to do this is by considering an isothermal expansion. Now you may recall that when we have an isothermal process, that means that my differential change in internal energy is just equal to zero. But of course, by the first law, that's equal to incremental changes in heat and work added together. My incremental change in work for such a process is just minus P dV. So that means that since this is all equal to zero, I can write my incremental change in heat as simply equal to plus P dV. And now I'm going to also put another restriction on this. And I'm going to say, let's suppose this isothermal expansion occurs, at least initially, under reversible processes. So as a reversible process, now I'll be even more specific and say dq reversible is plus P dmolar volume. But now I have this, I can relate this back to my entropy in this way. And in fact, I have ds is equal to dq reversible over t. And if I want to integrate these between 2 points, that means I'm integrating from 2 points of p dv. Now, this is going to be a little bit inconvenient because I also need to divide by temperature here. So I want to use my ideal gas equation of state to tell me about what this P over temperature would be. Well, I know that P times V bar is equal to RT, so if I rearrange this to collect P over T in one place, that's going to be equal to R over molar volume. So in other words, this integration that I've developed to calculate the change in entropy would simply be the change from V1 to V2. P over T now becomes R over V, so it'll be R dV over V. R is just a constant. I can bring it outside the integral. And I have my standard integral, dV over V. So that's just going to be equal to R log of the second molar volume over the initial molar volume. All right, now let's put a number on this. Let's suppose this thing is made to expand reversibly to twice its volume. So in other words, V2 is equal to twice V1. So that means that our change in entropy in this case has it's a number, R log 2. Now what I want to do is I want to compare this to what the result would have been if I'd done this irreversibly. So if I have an irreversible process, remember we talked about irreversible processes are in essence spontaneous processes. They're ones that we actually can't prevent from happening. They're just going to happen no matter what. So an example of an isothermal expansion into twice a volume that is irreversible would, for example, be the expansion of a gas into a vacuum that doubles its volume. So in that particular case, I not only have that the change in internal energy is zero, so that is du is equal to zero, but since it's not expanding against an external pressure, it's expanding into a vacuum, that also means that my work, the incremental change in work, is going to be zero. And I'm going to write that as irreversible because it's specific to this irreversible process. But since du is equal to zero and the incremental change in work is equal to zero, so is the incremental change in heat. So now if I were to write this out as delta S is, and I'm going to put a question mark over this, is a change from dq irreversible over temperature, what would I get? Well, if this is just zero, then this whole thing is going to be zero, and I end up with delta S is equal to zero. But now let me stop a second and say, if I have a state function, which I do with entropy, That means it should only depend upon the initial and final states. Well, in this irreversible process, let's say I've arranged it so that the final volume is the same as the final volume in the reversible process. And I'm holding both of them isothermal, so they're at the same temperature, and I haven't changed the amount of the gas that I have. So in fact, I should have that delta S is equal to R log 2 for both of these. This should be true not only for the reversible case, it should also be true for this. So what this tells me now is that it is not true that ds is equal to dq irreversible over t. This is not going to be the case. And in fact, since q reversible basically maximizes the heat exchange for this kind of process, what this really means is that the differential change in entropy is going to be greater than any irreversible process heat. So I'm always going to have this kind of relationship between the two. Now, generally speaking, if I just have some incremental change in heat, I don't know whether that's irreversible or reversible, and it could include contributions from both. So I may have an irreversible part as well as a reversible part. For the reversible part, instead of having this, I'm going to have an equal sign. But for the irreversible part, I'm always going to have this greater than sign. So that means that in general, I can write that the differential change in entropy is always going to be greater than or equal to the incremental change in heat divided by temperature. All right, so this is a really key result. I'm going to take it a step further, though, and note that since we have a state function, another property of state functions is if I evaluate them over a cyclic path. So we write that mathematically as this sort of circle around the integral. That just means we're following a cyclic path and we're returning to our initial point. Whenever we do that for a state function, we get 0. So now if I take this result and do this cyclic integral ds, I know that's going to be equal to 0. But I also know that this is greater than or equal to the cyclic integral of this path for irreversible. In fact, actually it's not equal to. It never is equal to unless it's got a reversible, if it's completely reversible. So I have, in effect, that for any heat change, an integration over a cyclic path is going to give me less than or equal to 0. This is a famous result called the Clausius inequality. And it tells us actually something important about systems. What we also need to know is that for an isolated process, all right, we're always going to be able to take something like this and generate a greater truth about entropy. And let me show you what I mean by that. All right, let's suppose that I have an isolated system and it's going between 2 points, A and B. And it's taking the first path is an irreversible path, but that irreversible path is also adiabatic. So in this case, I've got dq irreversible is simply equal to 0. That's what an adiabatic path does. Now I'm going to return by a different path, and the different path that I'm going to return by is a reversible path. All right, so this means that my dq reversible is not so constrained. It's not necessarily adiabatic. In fact, let's specify that it's not adiabatic. Okay, but it is occurring very slowly as a reversible process, to go back to the beginning. Now, if I were to evaluate the incremental change in heat going not only from A to B, but then back to A again, that represents this. And I already know that that thing is going to be less than or equal to 0. But I could also say that this thing is equal to the change from A to B of my reversible heat over temperature, plus my change from B back to A of my reversible heat over T. And now what do I have? Well, this part I know is equal to 0. So I just have this part left. All right, but what is this part? What is this entity? Well, I can recognize that this thing that I've written in the integrand is just ds. That's how it's defined. So if I integrate ds from b to a, what I'm going to get is sa minus sb. So if sa minus sb is less than or equal to 0, then I know that sa must be less than sb. In other words, the entropy content over here in state A is less than the entropy content over here in state B. All right, this is important because it tells us that for this irreversible process, even though the irreversible heat was equal to 0, there still was entropy generated in that process. And in fact, going from A to B, since the entropy content of B is greater than A, the entropy content for that first path was greater than 0. All right, that irreversible first path. Well, irreversible is also the condition that we have for spontaneous. And it turns out we can generalize this whole result to say that for any spontaneous process, this implies that in an isolated system, the entropy must always increase. Now, if the spontaneous process somehow is able to take place reversibly, then we might have an equal sign here. But generally speaking, this is going to be a true statement for an isolated system. And I guess as an added bonus, we could consider the universe to be an isolated system. So it will generally be true that for a spontaneous process, we must see the entropy content increase. And this important result is something we know commonly as the second law of thermodynamics. So we can see that there is a direct connection now between entropy and spontaneity in these systems.